First, I want to thank you for the invitation and warm introduction of us. So today, my colleague Gaurav Goyal and I will co-present one topic, and the title is "How is Conversational AI Platform Becoming a Digital Transformation Control Tower?" Next slide. Here's our agenda. I will start with overview, mainly including explaining the urgency for companies to implement control towers to speed up their digital transformation, and how the Servicenow conversational AI platform can help achieve the success on a larger scale. So to help you understand the value of implementing control towers, I will share a few customer success stories. Gaurav will then describe the architecture of conversational AI platform and explain several use cases that we implemented. Now let's start. So in the wake of last year's COVID-19 shutdowns, right, many businesses pivoted nearly overnight. And through that process, we all realized a number of long-standing assumptions about evaluating and prioritizing digital transformation were appended. So does customers still value the human touch more? Actually not. Digital experience can offer a more personalized, better personalized transaction than an in-person engagement. And customers are willing to pay full prices for digital services and products. For example, many of my friends signed up for Peloton membership. And to some degree, Peloton users are not willing to get out of from being immersed in Peloton digital services. So does regulation inhibit digital transformation? Here's the reality. Even highly regulated industry like healthcare are open to addressing barriers. Since COVID-19, many psychologists shifting to treat patients remotely. Can IT keep pace with digital transformation? Yes, of course, right? Because the tech industry, many business operations were kept going during COVID-19. So thinking that becoming a faster follower is wise may put a business at high risk for closures. So it is no longer enough to be on the trend of digital transformation. Business needs a control tower, which helps break down the data and the workflow silos. So similar to the aviation control tower, Servicenow conversational AI platform is a comprehensive command system, including 5 key functions. Our chatbot can connect to different bots to serve end users where they are. It could be web, could be mobile, or social channels. Our chatbot can also play a system role for live agent when there's a need. This is very similar in the AV systems. The control tower will connect to different pilots, connect to different planes. And one key thing in the control tower is providing the end-to-end visibility. And we have that also. So our conversational platform provides configurable analytics dashboard, provides insights into the workflow and the system records. The platform also empowers the chatbot to hand over the request to the live agent according to the different situation, manually or automatically. The platform runtime continuously monitoring the ongoing workflow and data to provide proactive alerts, very similar to the control tower in the AV systems will provide alerts for weather condition. So now how does it work? Actually, it's quite simple. There's really only 3 steps. The first step is to embark the journey, experience it, and explore it. So a business can embark on its digital transformation journey by following the guided setup with just a couple of clicks. And then they can quickly experience itinerary through the purpose-built conversation topics. That spans IT, employee workflow, and customer workflow. The topic recommendation module allows companies to explore their systems to identify new critical flows to be automated. The second step after you have basic control tower is to optimize it to deliver services anytime, anywhere by adding a new topic flow, conversational flow. So Virtual Agent Designer provides a graphic interface that enables anyone to drag a job to create the flow. And through the accumulated conversation transcripts, the NLU workbench can help to improve the NLU and machine learning model. The incident auto resolution, live agent handout, as well as agent autopilot, all together to facilitate agent work along with the chatbot or work with their agent co-works. As I mentioned before, providing end-to-end visibility is very important. So the conversational analytics dashboard provides in-depth insights as well as the visibility as whatever you are interested. The last step to speed up the digital transformation, it's important you include the solution into various business user cases. The bot-to-bot API allows the company to unify different business chatbots into one unified experience, even though behind the scene you may have discrete systems. To serve end user where they are, a company can choose specific channel integration plugins available at the Servicenow store. And the Servicenow, the agent designer natively integrated with Servicenow Flow Designer. So a topic author can use one of the pre-built integration spokes to pull in the third-party system records. At this point, you may still wondering what is the benefits of implementing the conversational AI platform as a control tower. So I would like to share one story here. University of Maryland is a state's flagship university and one of the preeminent public research institute. They have more than 41,000 students and 14,000 faculty members. The mission is to provide an excellent environment for teaching, researching, and study. However, their current system is purely based on email, based on siloed workflows. So they implement the Servicenow conversational AI platform. And that helps them to achieve some successful metrics. Because of the predictive intelligence and excellent routing aging, they're able to achieve 7% reduction in the incident resolution times. At the same time, achieve 66% reduction in incorrectly incident routing. Because our virtual agent can help deflect incidents, so they are achieving 25% incident volumes. Their architects is super happy with the experience. Considering time, I'm not going to another success story. Instead, I'll pass the presentation to Gaurav.
Thank you, Wendy. So I'll take a quick deep dive into our conversational AI platform architecture. So if you see here, for any conversational platform, you have seen this in the market time and time again, that we have platforms built for a specific need or specific purpose. But Servicenow being a platform company, we want to make sure that we not only provide world-class experience to our customers, but at the same time, we provide them enough configuration option that they can build or enhance our platform to their needs. For an example, the same platform can be used for B2B partners or B2B customers, and the same platform can be used for B2C customers. And technically, with very few fine tunings, you can very well use the same platform across. And how does this conversational AI platform work? We do out of the box support web client, which is something which we ship out of the box. Then we have our iOS and Android based integration. These are the mobile apps what we have for VA or virtual agent. Then we have multiple bot-to-bot integration supported, where you can have any bot. So if you have invested in one third-party bot integration framework, you can very well just connect that with Servicenow out of the box. Plus, we have a bunch of channels. We are making our VA or conversational interfaces platform voice first. On top of that, you can bring your own adapter or your channel. So the way it works is, from any of these channels, when we send the messages or when you do the handshake, first it goes via REST API. All the incoming messages will be queued up. From there, in the asynchronous way, we will be pulling these messages, and then we will be doing some inbound transformation, because when the messages are coming from different channels, they might be having different formats. So we need to do inbound transformation to transform into a common format which our state machine understand. Then our state machine will work on that particular message, do the topic discovery. And for topic discovery, we have via integration hub, we do make a call to some third-party NLU providers, or we can use our own NLU internally, which is available in now Servicenow NLU. Based on the NLU, we detect the intent entities, which is very common in industry, and then we pretty much get the intent, and based on the intent, we find out the dialogue or the topic which we want to execute. Based on the topic execution, state machine will get a message out. We will do the respective transformations. And if it needs to be sent out to one of these channels or the bot, we will send it via the REST API call. But if we have to do this with our native integrations to our web client and mobile apps, we will be doing via the asynchronous message bus. And we will be having a WebSocket connection open up for the web client and the iOS and the Android application. So this is for the virtual agent integration. But at the same time, if at any point customer wants to route to live agent via automated way, we use AWA, which is our agent work assignment, which is a complex engine what we have built, and users can manually ask to route to the live agent. We do have agent assist, we have agent autopilot, and some of these I will talk through in the next slides. On top of that, we have a bunch of admin capabilities, which Wendy has already talked about. We do support 90+ KPIs on our analytics platform, and this platform is completely configurable by our customers, and they can change, add any charts, any KPIs they want on the runtime. And we have a bunch of ML trainings are going based on this data. So let me jump on to the AI use cases. We have something called an incident auto resolution. What we do is our main agenda is to deflect as much as we can. And for that, we are using our AI and machine learning to the extent where is possible. So what we do is, as soon as the incidents are created, we try to assign those incidents to the virtual agent itself. Virtual agent will run through this predict intent API and try to find whether it can resolve this incident itself. And if it does, if it's beyond a certain threshold, we assign these incidents over to the virtual agent, where virtual agent will send a proactive notification to the customer on their preferred channel. And from there, customers have a choice to continue with VA for this incident, or they can decline. And if they accept it, they can very well continue running through this topic, and VA can solve this problem, and where we can mark the incident as resolved. So what we are trying to do here is we are trying to proactively deflect incidents before some live agent have to work on it. The second use case is bot-to-bot communication, which we talked about. In here, we have built a kind of an ecosystem of bot frameworks, where we have something called as a primary bot, which can interact with n number of secondary bots. And we understand the customers or the companies have invested in multiple bot frameworks today, and they don't want to get away with that because they have already invested a lot of knowledge as well as the data on those bot frameworks. So what we have done is we built an ecosystem where we can work as a primary bot and provide a facility where we can serve for as a primary bot and do the NLU at the upfront, or we can send it to any of the secondary bots. And I can definitely do a drill down into the next session. Similarly, we can do a live agent transfer via the same framework if it is possible. Next is a topic recommendation. Topic recommendation is another ask in today's world. When some new customer comes and want to use any virtual agent and chatbots, they have bunch of data in the form of incident cases, which is sitting in their instances. And now either we can ask customers to identify, look at their data and come up with the prerequisite where they can create their own topics and their own dialogues. Or on the contrary, what we are doing is we are using some of the machine learning and AI capabilities by identifying some of the recurring incidents or recurring topics. And then we are suggesting those topics over to our customers. So as soon as they install our virtual agent, we also have something called topic recommendation, which tells them, okay, if you use these 7 or 8 topics, there is very good chance 30% or 40% of your cases can be resolved. So we are doing this as a proactive during the installation process itself. And another use case what we have is Agent Autopilot, where we are trying to save time for our agents, where if agents are getting lots of requests and some are very repetitive in nature, and sometimes customers don't want to talk to a virtual agent and want to directly go over to the live agent. In those scenarios, as well as if there is some sensitive information which we don't want live agent to capture, sometimes like credit card information or SSN, etc., etc. In those scenarios, we are providing a way for our live agent to start something called as Autopilot. At that moment, they will be bringing their virtual agent in the mix and handing over that particular conversation to virtual agent. Virtual agent will collect some information. Now customers can either close the chat at that moment, or they can hand it over back to the live agent if they want to. So we can definitely have more details coming in.
All right. Hi, everyone. My name is Sanaz Bahargam. I'm an applied scientist at Amazon Alexa AI team. And today I will be talking about Alexa Conversations, which is an AI-driven approach for creating task-oriented dialogue systems. So I would like to start off by talking about what are the skills on Alexa. You can think of skills as different capabilities that Alexa offers, and these may be experiences that are built by Amazon internal teams, partner Amazon teams, or even external developers and companies. Today, there are more than 100,000 skills on Alexa. Reaching customers are more than 100 million Alexa-enabled devices. 4 out of 5 Alexa customers with an Echo device use a skill. There are hundreds of thousands of Alexa developers building skills that are available in over 80 countries and 15 languages. Skill builders are creating innovative experiences by using Alexa's automatic speech recognition and natural language understanding technology to let people use their voices naturally to interact with content, services, and devices. There are 2 broad categories of interaction with Alexa. The first one is one-shot interaction, and this is really where Alexa started, and they have driven a lot of growth in Alexa. These are the interactions where the user goes to Alexa and says, do X, and Alexa does it. The user gives a command, which is interpreted and sent it to the backend, which does some work and sends back, and I'm done confirmation. For example, here we see a couple of examples. The first one is like, Alexa, set a timer for 10 minutes. Alexa, turn off the kitchen lights, or Alexa, what is the weather today? So for these interactions, there is always an intent coupled with it, and the developer believes that the user's requests represent that intent and the corresponding statements that the user may say. This is used to formulate a backend model representation for understanding the user, which works really well for one-shot interaction. On the other hand, where we see a lot of innovation turning to in the next several years in Alexa is around multi-turn interaction. Multi-turn interaction allows Alexa to have a more in-depth interaction and a lot of back and forth with the customer to really understand what exactly is what the user is trying to achieve. The core of this presentation is about multi-turn interactions. And here you see an example of this for a pet matching skill. So in this scenario, the user starts very broad by asking what dog breed is good for me. This is a very broad question. Alexa needs to filter down the search. So it starts by asking what are the 2 things that you're looking for in a dog. The user replies back with, I want a big friendly dog. So in this case, Alexa can actually filter down the search. Again, it can actually ask more questions to narrow down more the search. So it asks, do you prefer high energy or low energy dogs? When the user says high energy with the 3 pieces of information, big, friendly, and high energy dog, Alexa can start a recommendation and can say, so a large, friendly, high energy dog sounds good for you, consider a Labrador Retriever. So what you see here is the customer starting out super broad, and there are a couple of back and forths until we can narrow down the search and gets recommendation to the user. So this represents a multi-turn interaction when there's a bunch of back and forth between the user and Alexa. And this is where I mentioned that it's the focus of the presentation, and there are a lot of innovation here. Another example is for purchasing movie tickets. So user here in this example starts by saying, what are the show times for Dark Phoenix? And Alexa returns the results by saying, here are the show times for Dark Phoenix, 10:35 on Saturday, June 8th at Regal Cinnabar Palace Station. The next one is 8:30 on, and so on and so forth. So when the user says, get me 2 tickets for 10:35, the user just talks about the time and doesn't say anything about the cinema. However, by saying the time, Alexa can actually understand what is also the theater that the user is interested in, and returns back 2 adult tickets for 10:35 show on Dark Phoenix on Saturday, June 8th. Will be $21. Should I book the ticket? So this is actually an example of entity resolution and disambiguation. And here we see an example of a mixed initiative. When Alexa says, should I book the ticket? User actually, instead of going to that direction, user stop and saying, wait, how long is it? And Alexa goes back and says, Dark Phoenix is 1 hour and 52 minutes long. So here, both parties are engaged in the conversation, and they have the ability to drive the conversation in any direction they want. So Alexa is actually going down the path of completing the task, which is purchasing the ticket. However, user actually drive the conversation in another direction by saying how long is it, and they may actually change their mind and want to do something else. After getting the duration, user says, actually, what are the show times after 7 p.m.? And the user, the Alexa says, here are the show times for Dark Phoenix on June 8th after 7 p.m. So in this scenario, there's this concept of having the context. So the user is only asking what are the show time after 7 p.m. And doesn't say which movie. So there is this notion of capturing context and returning it through the dialogue. This is something that we as humans, we do it really well with the ability to compartmentalize our memory with short-term and also long-term data. For virtual assistant though, context is a much harder problem. Here you see Alexa is able to actually track that. So at the very end, when the user says, what's the show time after 7 p.m., she's able to refer back to the earlier part of the conversation where there was a discussion around looking for movie times for Dark Phoenix without the user having explicitly saying the movie name. So all throughout this conversation, there is this context that's maintained, and the user and Alexa are able to refer to elements of the context in a natural manner and carry out the conversation forward. All these 3 things that I mentioned are fairly complicated, but it's very well done in Alexa, and I will talk about how it's done. First, I would like to talk about the dialogue simulator when I'm talking about the technical different components of the Alexa. So I talked about developers, and I talked about they provide, for example, some functionalities for the user, such as purchasing movie tickets or booking a ride. So when they partner with Alexa, they provide the APIs. The APIs are the things that are actually completing some tasks, for example, purchasing the movie ticket. They also provide possible slots for those APIs, like, for example, what is the possible value for the city and the dates when the user is asking about the weather. They also provide response templates and sample dialogues. However, they only provide sample dialogues, something around a few of them. And this is not enough for training our model. So what we do is that we actually generate more dialogues through simulation. So the first thing that we do is we generate different dialogue flows, something around 100 dialogues. Then we send it to another component, which is automatically generating natural language variations through paraphrasing. And at this point, from 100, we go to something around 10,000 examples. Now we have enough data for our training, so we can actually use those dialogue simulations for training. So from a few examples, we went to 10,000 examples. Here we see the simulation of a dialogue in more depth. So I mentioned that the user has a goal to achieve. So in this scenario, the user is informing the goal by saying, what's the weather? After this, Alexa knows that it should call get the weather. However, it's lacking the slot values, which in this case are city name and the date. So Alexa says which city and for which date. User says Seattle today. So in this case, the action that the user is taking is informing the slots value. The next step, Alexa confirms the values. So it says, just to confirm, you want the weather report for today in Seattle. The user can affirm or deny. And at the end, now that Alexa has all the required arguments or slot values, it calls the get weather and sends back the results to the user by saying today in Seattle, it's a high of 70 degrees and a low of 60 degrees. You see one possible path for getting the weather. However, there are many user behaviors and we need to actually simulate them to make sure that our model are robust to all of the scenarios. Here I'm showing 3 different examples of user behaviors. The first one is a more cooperative user. So when the user is asking what's the weather and we ask for the city, the user provides both the date and also the city. On the middle, we see a less cooperative user. So when the user asks for the what's the weather and Alexa asks for which city and date, the user only provides a date. And also it's possible that the user may change their mind in the middle of the conversation. So when the user is asking what's the weather in Seattle and we ask for which date, the user says, no, actually in Boston. So these are these different behaviors and we need to take into account all of them. The way that we do it is that from the provided dialogue, we actually do catalog sampling to provide more training data for the model, and we provide simulated dialogue. So for example, for the city here, these are the catalog that is provided by the developer, and we sample some values from here to replace it with Seattle. So we can say instead, what's the weather in New York today? We can do exactly the same thing for other arguments or for all of the arguments. So what's the weather in Seattle today? It's going to be what's the weather in New York tomorrow. We can also change the order of the arguments. And finally, we can actually change the surface form of the question by sampling from the sample utterances or through paraphrasing. So what's the weather in Seattle today can be how does the weather in Seattle look tomorrow? Now that we have a good understanding of the how we generate the data for the model, let's talk about the models. The first model that we run in the flow is an NER model or name entity recognition. So NER model recognizes slots or entities in the user utterance. Entities are defined by the developer and are backed up by the catalogs of entity values. The entities are units of information that we need to pass to the APIs and response templates. For example, date and city. When the user says Seattle today, we run the NER model. The NER model knows Seattle is a city and today is a date. So for this, we apply turn level and dialog level feature extractor to extract features and pass them to the context encoder. We also extract catalog features based on the catalogs provided by the developer. We concatenate feature representation and concatenate them with the word embeddings, and we pass them to a BERT with a BiLSTM model. The second thing that we run here is the action prediction. The action prediction model predicts what is the next best action that Alexa should take given the user utterance and the dialogue context. In this scenario, when the user says Seattle today, after recognizing the name entities, we run the action prediction model. So the action prediction here is confirm get weather for the given city and the date. When we run the action prediction, there are some arguments. Confirm get weather needs some arguments or values, which we fill those arguments with running another model, argument filling, or AF for short. AF model fills in the values of the API and response templates for the input arguments, looking at all the dialogue context so far. It picks the values by looking at the compatible entities in the dialogue that the NER model recognizes earlier. After both action prediction and argument filling models are run, the actions are and arguments that those models decide will always be valid. For example, Alexa would never decide to do an API if a required input argument of the API has an empty value. Argument filling model is a variation of neural comprehension model, which is an attention plus pointing mechanism. And we impose some constraints to only fill arguments with the slots that the correct type, with the slots of the correct type according to the action schema. So when we run these three models for each utterance, we send back some results to the user, and we run these again and again. To evaluate our model, we evaluated on a movie ticket purchase dialogue, and we have 50 test dialogue. In each dialogue, on average, we have 7.7 number of turns. We evaluate on two settings. One of them is when we only use language variations, and the other one is when we are using language variation and also different dialogue flows that I mentioned earlier. We also evaluate when we have only 1,000 number of dialogues versus 10,000. We see that when we go from 1,000 to 10,000 in all of the scenarios, the performance of the model is improving. And also we see that when we are using both language and dialogue variation, we see the model is performing really well for NER, for action prediction, and also action signature accuracy. I think I talked about NER and action prediction. Action signature is when both the action and all the arguments are predicted correctly. In order to summarize, I showed how Alexa conversation is being done. This is a novel data-driven approach which lets us build goal-oriented conversational experiences in an end-to-end manner. I also showed that our proposed system significantly reduces the developer burden while still allowing them to build robust experiences. Also, currently and also in the future, we are aiming to reduce developer requirements for providing energy responses by introducing a statistical energy system in the future. We will also develop robust mechanisms for incorporating the developer feedback through supervised and semi-supervised methods to improve the performance of our simulator and our modeling components. Thanks a lot for listening to my talk. We are also actively hiring, so if you're interested to work with us, please contact me. Thank you.
Hi, Al. This is GP. Thank you very much for the host for having me on this conference or providing me the opportunity. Primarily today, I'll be going over the. This is actually a book that I published, and based on various algorithms that I implemented, and long ago I've written some dissertation as well on machine learning, deep learning, and also some of the stuff from there and everything else. And this book it already has released a week ago, and it is available right now on Ex Libris, which is the book publisher. It's also pushed into all the online bookstores like Amazon, Barnes and Nobles, which will be available soon. So primarily, the objective of this book is, to provide a foundation for all the machine learning practitioners and deep learning practitioners. The book covers several algorithms, including machine learning algorithms, deep learning algorithms, and supercomputing and high performance computing, and several other implementations of algorithms, including natural language processing, and neural network architectures, reinforcement learning algorithms, supervised, unsupervised. And all of these algorithms have been implemented in PyTorch, TensorFlow, R, and Python. It depends, like if there is a heavy leverage of statistics. So initially I go over all the statistical equations, and then I'll cover the chapters for implementation in R with statistics. And then again, I also cover reinforcement learning algorithms, and reinforcement learning algorithms is where primarily I provide all the foundations of reinforcement learning, mathematical equations with Bellman and other equations as well. And then I will go forward with actual implementations of them in PyTorch. So the primary expectation is for people to have some preliminary understanding of mathematics and statistics and programming languages like Python, PyTorch, or TensorFlow. Like even if they are not having very advanced skills in it, like they have some basic understanding of object-oriented programming, and they also have some mathematical background, that will be sufficient. But I ensure that for people who are not having a lot of background on linear algebra as well as the calculus, I tried to introduce as much of chapters where I could introduce them to take them over to the fundamentals of it, just so that it all comes back. I'm sure like most of the programmers have worked on a lot of mathematical equations, but then again, it's not something that they perhaps have implemented in the recent times. So if that is the case, also it helps them to refresh their thoughts around it, so that they can be prepared for implementing machine learning or deep learning projects. So in the actual session, which will be happening in a week from now, I will be having a more in-depth coverage of all of the components of architectures and deep learning and machine learning. Today, I'm just going to go over just to fundamentally give you an overview of what we're going to be covering. Again, this book is available for all of you, and it will be available in Amazon soon, because right now it's released on the publisher's book site, and it's going to be there very soon. So let me give you a brief overview of what we're going to be covering in the upcoming session. So we're going to go over the neural networks to understand like what are the neural networks. Like we have had several architectures from several years. Like if you start from the like 1950s and then coming to 60s, 70s, 80s, and so on and so forth. So when we spoke about all of these architectures, people have different ways of implementing artificial intelligence. People have built several machines with millions of rules and hash-coded algorithms and several ways of implementing this, but they did not have any technical architectures like we are talking about Boltzmann machines or autoencoders, or any other type of neural network activations and so on and so forth. All of the deep neural networks, because back in the day, like people have been implementing like Bayesian neural networks, mostly limited in terms of how many layers you can actually have inside a neural network, because people can have like 2 neural networks or 3 neural networks, but when the deep neural networks have evolved and were introduced only like 10 years ago, has significantly revolutionized the number of neural networks that can be introduced. It could be like thousands of like 10,000 neural networks. And again, especially if you're looking at generative adversarial neural networks such as GPT-3, all of these architectures have been built and running through so many of neural networks. That's the only way like we can have the outcomes you are looking at, a large scale processing, large scale text, and ability to even write an article by AI by itself, or building like a Wikipedia by AI. All of these achievements that we are seeing in the AI is possible through processing through deep neural networks. And again, it's a generative neural network that has been leveraged on text processing features like that. So that's what we're going to explore, the natural language processing techniques, how we can implement it. We're going to process a lot of files that contain large volumes of information encoded in it, like, for example, like Amazon reviews or any other, if you want to build a word cloud or classify a lot of text information, and something like, you can go over all of the samples from GPT-3 and see what it has achieved. All of these accomplishments we can go through with Python, with the libraries such as NLTK, GenSim, Spacey, a number of libraries we can go over, and we'll see how that is implemented in Python. And we can also go to reinforcement learning algorithms with PyTorch, and statistical and machine learning algorithms in R as well as Python. And TensorFlow is where I've leveraged TensorFlow primarily for covering, mathematical, equations and anything like, where we have high precision and floating pointers, or we want to process something like, in scientific engineering, supercomputing, high performance computing, all of that stuff we can accomplish through TensorFlow, because we have tensors in it, which are multi-dimensional arrays. And so those can process any number of mathematical operations, especially for multi-algebraic grids that we want to solve, or we're going to solve anything like Navier-Stokes equations for aerodynamics that we want to build, and run some processes and simulate how we can build aerodynamics for plasma turbulence or nuclear fusion or any of such things. All of these mathematical operations can be implemented, and that's what we're gonna go over. And again, as I mentioned, like, it's very important that we activate neurons in a neural network to be able to actually pass the information from the neural network as an input, and then we're going to process it with the layers, the hidden layers we're going to have in it, and then we're going to process it and produce the outcomes from it. Again, we're going to have a lot of gradients, and we have had problems with vanishing and exploding gradients, especially if you're going to implement like any optimization algorithms, you're going to have issues. So that's when we can actually introduce techniques like ReLU, which is a rectified linear unit. So whenever if you're building APIs for passing through all of these neural networks for any Xavier initialization or any other neural network techniques to activate, like for example, we have sigmoid function. We also have hyperbolic tangent function, which is also known as tan, TA, and H. So all of these activation functions we can leverage to activate the neurons, and then it's going to connect to the node, and then it's going to pass the information. And again, whenever this entire process happens, there will be some amount of error, which will be probably not much, because if you're looking at the weighted sum, you find it like, a very narrow error there. But again, that's what we call the back propagation, so that we can go back and fix the errors in it with the back propagation technique. And again, for activating any of these functions like sigmoid or hyperbolic tangent functions, you necessarily don't have to build these equations and apply it from scratch, because this is something that has been applied with a lot of built-in functions from R, Python, PyTorch, and TensorFlow. Especially PyTorch and TensorFlow have a lot of functions, including the rectified linear unit we are talking about. So we can leverage the libraries, and we can leverage the built-in functions to activate these linear transformations in a hidden layer. And then we can also activate a particular neuron, and then we can transfer over the information from neuron to neuron in the node. And then we can activate the neuron. So that's what we can achieve through these functions. For example, if we were to take a look at this, so we have a Z1, Z2, Z3 as inputs, and then we have C1, C2, C3 as these hidden layer here. And we also have an output, which is also a C. So whenever we take these neural networks, we pass through the input, which is a Z1, Z2, Z3, then we can represent a bias node as well. So we're going to take a look what is a bias node is shortly. So in the bias node, what happens is primarily we will be introducing a few more nodes here, which will be also be considered in the weighted sum, so that whenever we initialize with some random values, so that we're going to have more fair outcomes on the calculations we're going to be performing. Whenever we do the summation of the weights, we're going to have a proper activation, so that it's not going to have any bias, because if you're going to initialize with a particular values, it's going to give you some bias. But the way that we're going to be implementing is actually through activation of neurons by randomizing the initialized parameters, so that we're not going to have any bias in the neural network. And again, the vectorized calculation occurs for the inputs whenever we use stock of the parameters of the neurons in the neural network. So again, so as I mentioned, TensorFlow is a machine learning library, and it has been leveraged as part of Python, so you can even invoke it. And initially it was founded, and it was only leveraged by Google for their internal research labs. But then again, they have completely released this for all of the enterprises to leverage, so people can actually start leveraging the TensorFlow and start implementing it for their high performance computing applications. And then you start building a lot of HPC workloads and supercomputers. Again, as we have seen in the recent times, the conjugate gradient solver has been addressed. Fast Fourier transform or stream or matrix to matrix multiplications with large number of multidimensional arrays. It's not like we're going to have some set of normal matrix, but the amount of information that you're going to be dealing with, especially for plasma turbulence or particle physics, is going to be larger. And so that's when we're going to actually be implementing TensorFlow applications. And there's also, CUDA support for parallel programming and OpenCL MPI, which is a message passing interface, which is part of the high performance computing, which is written in C, C++. We can leverage that. We can run all these applications and wrap up the whole module in TensorFlow to run on a TPU or a GPU. Again, the prerequisites when you are coming for the next session, please ensure that you have either a Google Colab that you can leverage to run all of these applications of TensorFlow, or you can also export a Anaconda application, and then you can run through the Jupyter environment for it. That's another application that you can leverage. So that you have multiple options, either come with a Google Colab or come with Anaconda Jupyter environment. Either of them will work for you. I'll send more information out for coming up with that. So we're going to have some workshops and hands-on sessions where I'm going to primarily be covering some topics where we're going to be going through like this, and then we will actually, I'll give some exercises, you can perform it, and then I can show you if there is any error in it, or how I can help you to resolve those errors, and we can run the outcomes, and we can get what we require to get the outputs. I'm gonna provide you that for you as well. So again, we'll be covering scalars, we'll be covering the tensors, multiple rank tensors, rank 1 tensor, rank 2 tensor, and so on and so forth. How do we multiply this information, and how we can shape a tensor, how we can change a tensor shape. Like for example, if you start with like this, how are we going to be able to transpose it? How we can change the shape of a tensor, we can get the output we want to get. So we can look at that. We can come up with such information. We're going to run some matrix multiplications, and you can see how we can multiply linear algebra, linear algebraic equations that you can perform in TensorFlow. You will be actually running everything hands-on on this session. Of course, I'll be covering the theory, but then we're going to be running the programs, and we can get in the outputs, and we can fix all of the issues that we're going to have throughout the workshops. We're going to validate and verify the outputs that you're going to get, whether it matches with the program, or are there any issues that you guys are having, and we can go over to resolve it. We're going to be covering the Moore-Penrose pseudo-inverse as well, how we can actually implement in TensorFlow. And then we will be running the programs for it. We'll be also going through the singular value decomposition, which is a billion-dollar algorithm. The reason why we say is many corporations, like for example, Amazon implements it, Netflix implements it, all of them implement the singular value decomposition for building the REXs, which is a recommendation system. You might be wondering, oh, I want to purchase this book and I'm able to get this outcome. And then you would be wondering, how did I get this recommendation for this book that you looked at, right? So that is because of the singular value decomposition that is available, that provides you all the recommendation systems. So we're going to go over that, see how we can actually implement the singular value decomposition here. We run through our programs and we get our outputs, and then we can see how we can actually build this Rexes. And we're going to go over the calculus, and we're going to go over the fundamentals, because as I mentioned, my book is about not just giving you advanced options of implementing the equations, but setting up from the fundamentals all the way, so that you're going to get how do you perform, what is a calculus, how do you perform numerical computations, what is automatic differentiation. Is it something that we have to manually calculate in a program, or can we leverage any modules for automatic differentiation? What is the a forward differentiation? What is a backward differentiation? And what is a Jacobi matrix, what is a Jacobi, matrix calculus, for example. So Jacobi matrix is also known as matrix calculus. How can we run and achieve the matrix calculations, and so how we can perform all of these equations, and how we can leverage the gradient tape APIs in the TensorFlow, how we can implement the gradient API in TensorFlow and all that. So we can take a look at that and how we can implement that. And how can we implement the calculus chain rules? We're going to go over that. We're going to run some sample. We can see how we can run the chain rules. And we can also run all the calculus equations, and we can, how do we compute the derivative of z, and all of that stuff. We're gonna go through that. And again, back propagation, I'm gonna primarily cover the more, because if you're gonna leverage any built-in function, it's gonna be easier for you. But what I would like to cover for you is more like the entire architecture of back propagation, entire the mathematical equations of back propagation, how we can perform this, how we can achieve this. You can implement this in PyTorch, or you can implement in Python, or in leveraging neural networks. And here is, how you can implement a back propagation. We're going to go over with an actual example of a back propagation for this. We're going to run through some samples.
It's okay.
Yeah, and we're going to run through some samples to see how we can get the back propagation, and how we can build these outputs, how we can get that. Again, we're going to have a workshop started, but I'm just going to go over, because we can't practically run all these programs right now, either in a Jupyter environment or in a Google Colab right now. So that's why I'm just going to go over that. So this is what we're going to have. This is just a preview of what we're going to have. If time permits, we can also go for reinforcement learning algorithms, as well as supervised, unsupervised machine learning algorithms, and deep learning algorithms, and also statistics. And then again, how we implement that in R, all of these algorithms. So that is something where, this is what, briefly what we're going to be covering. We're not going to actually be covering right now, because this is going to take time for us to set up the environment, run the programs, and go through each function and all that.
Great. Thank you so much. Thank you for the invite. And as was mentioned, I'm working as a product manager here at Mass General Brigham and developing AI solutions in healthcare. And the idea today is to talk a little bit about multimodal AI in healthcare. So here's the outline of what we'll be covering. First of all, concept and motivation behind multimodality. How can we create such solutions? The impact we can have, and some of the challenges that we face in this scenario. So first of all, what are we talking about when we say multimodality in healthcare? Healthcare, by definition, is a multimodality system. We have different sources of data from different modalities, which can be imaging or non-imaging, like radiology, pathology, endoscopy. We have waveform data, we have lab tests, we have clinical notes, we have several different types and sources of data within healthcare. And it's very common to have multidisciplinary teams in healthcare, and each professional is specialized in one type of data, one way to look at the data, and then we combine the different knowledge from different professionals to arrive to a better diagnosis and patient management. So just to give an example here, like a single healthcare professional cannot master all areas. So here we have, just as a diagram, different physician specializations. And there is an overlap in knowledge in terms of a radiologist is going to know a bit of internal medicine, pathology, and so on, but it is impossible to master and have the same depth of knowledge in all areas. And therefore, can AI help us have this broader view and integrate all those different data points and different knowledges? But how can we, first of all, from a technical standpoint, do this? There are several ways to combine data sources. This is like a technical solutions for that exists. Just here are some brief examples. We have images showing two different data sources, one in blue and one in green. You can see in the first image, for example, where the data sources are concatenated into a single feature vector, and then you develop a machine learning model that takes this combined feature vector as an input. For example, on the side, we have data sources that run through different machine learning models that extract features from both data sources, and then the extracted features are then fed to a new model. So there are several ways, different methods that you can use to actually combine data from different sources and different modalities. But how can we do this in the real life? And what I want to talk about here is about the potential impact of developing those strategies and some of the challenges that we will face ultimately when developing those ideas. And I'm going to go through with more details in the next slides. So first of all, to discuss the impact, let's imagine a patient that has a radiology data, has lab tests, and has a medical history. This patient might have a chest computed tomography, a chest CT that was taken. He might have a hemogram, a very common blood test. And among the medical history, you might have the history, like the comorbidities that the patient has. And going to a level deeper, this chest CT might have a lesion that we call like a consolidation that has a clinical meaning. This patient might have in the hemogram, is going to have the white blood cell count. And in the comorbidity session, you will have the information if the patient is diabetic or not. And by using something, creating a solution that is multimodality, you can basically evaluate how all those different factors interact with each other, and you are able to develop machine learning and artificial intelligence solutions that can generate more abstract predictions, more abstract outcomes. For example, you can do something that will estimate the risk of a patient being admitted to the hospital. You can estimate how long the patient will stay at the hospital, risk for mortality, and all because by having different data sources, you have a more complete picture of the patient. But that being said, there are several challenges in actually implementing those solutions. So first of all, in terms of data sources, radiology exams are usually stored in the PACS system, and while lab tests and medical history are found in the EHR, the Electronic Health Record System. And that information can either be structured tabular data, like lab tests, or it can be unstructured, it can be clinical notes. And this is just to give examples based on this hypothetical scenario that we have. And it's going to be difficult, challenging to create something that has access to all those different data sources and can properly process all those sources. And especially if you have free text and clinical notes, you might need a natural language processing way to actually extract the information you need. Going to a different factor that needs to be taken into account is the temporality. Basically, when you develop a model, data in healthcare, they will not be taken at the same time. So a chest CT and a hemogram, they won't be taken simultaneously. they will have some time difference. So a chastity and a hemogram that were taken less than 24 hours apart will have a very different clinical meaning compared to a chastity and a hemogram that are taken 1 month apart from each other. So once you design such a solution, you have to take this into account. You might have to establish a threshold, a time frame that you're going to look at, and only take that time frame into consideration when running inference in your model. The next challenge that is worth mentioning is about missing values. Every patient is different. Not every patient is going to have every information available at the same time. Even for a specific condition, it is common that patients will have different information available. So let's say in this scenario again, what would happen if the patient doesn't have a chest CT? Or in the other hand, let's say if the patient only has the chest CT and doesn't have the information about hemogram or comorbidities, would your machine learning solution or model still be able to run? Will you have a minimum number of variables that need to be available in order for the model to actually succeed? Are there required variables and optional variables? How will you handle missing values? And if you have a large number of missing values, does this impact the performance of what you're delivering? So all those aspects need to be considered. But let's say you moved on, you designed your algorithm, your model, and you want to implement this into real setting. So there are challenges in the implementation as well. In terms of the data sources, as I mentioned before, you will need an orchestration system that will feed the relevant data to your model. And often this pipeline needs to be hospital specific. So you need infrastructure, you need support from IT to actually have those things in place. And then once you go to a model per se, how are you going to run this model? Will your hospital system have on-prem GPUs to handle all these different types of data, especially imaging that can be very expensive to run in terms of computational power? Will you use cloud solutions and send your data to be processed elsewhere? And if that's the case, how will you handle privacy concerns? How are you going to ensure that the data is de-identified? Does your government allows you to do this kind of process? And finally, once you have the output, how will you provide this output back to the healthcare professional? It's important to have this implemented in a way that is coherent, that is integrated with the clinical care. We want to avoid having the healthcare professional go to a separate system, to a separate app, to a separate website, just to check the output of AI models. Another challenge is in terms of interpretability. Most common AI models, they are kind of straightforward, and the healthcare professional can easily check if the output is correct or not. If you have an algorithm to do lesion segmentation or detection of diseases, classification models. If you are doing multimodal solutions and more abstract outcomes, as I mentioned before, for example, length of stay, it might be tricky or more difficult for the healthcare professional to trust that output. So as potential approaches, you can try to explain what the model is considering when doing the evaluation, like saliency maps or mentioning the feature importance of each of the variables, and perform several validation studies to actually gather confirmation that the predictions are accurate, and also to build trust within the healthcare community. So as a conclusion of this preliminary talk here, basically the existence of this big data and a large amount of healthcare data associated with the computational power that we have allow us to basically design and start implementing multimodal AI solutions. And there are several challenges to this implementation, but the potential impact in healthcare patient lives is huge. And this is for sure a step into the direction of personalized medicine, where your individual patient data is considered when doing the patient management. So yeah, thank you so much.